Welcome to the very first compilers reading group. Today's paper is 2 Decades of Smalltalk VM Development, Live VM Development Through Simulation Tools by Elliot Miranda, Clement Barra, Elias Gonzalez-Boix, and Don Ingalls. I guess before getting really started about discussing the paper and all that, I kind of want to give a very, very rough summary of what Smalltalk is, as it's not a really well-known or well-used language in the modern day, sadly. Smalltalk was an object-oriented language made, I want to say, back in the 70s. It was, I think, designed for kids to use. It was designed for a kids' educational language and trying to do everything through an object-oriented model, kind of like their view of what future programming was like. And as such, it has a lot of features of an operating system, right? Things can change on it. Like you make objects, and these objects exist, and you can add new ideas to built-in objects. The language is quite minimal in that the entire syntax fits within a posted card node. So it's a rather small language, but it gave birth to really big environments. And if anyone's ever used an IDE, you can probably think a lot of its features coming from the genetics of Smalltalk. And so that's kind of where this comes in. And the paper deals with the various virtual machines found within Smalltalk, namely an open source version that projects like Pharaoh and Squeaks and Newspeak all use. I'm kind of new to this book reading format, but I guess how we'll probably open up is I'll probably cover give a really rough summary of the chapters of the book, and then we can open it up for discussion. If that's cool. We'll, I guess, begin there. So this paper is kind of broken up into 3 sections. The first section, which is section 2, deals with the machine itself, like what is the virtual machine that they designed. Section 3 kind of covers their experience reports, and section 4 just covers how does this relate to other projects in the space. And they don't talk about it much in the paper, but I can give some pointers to what they referred to because I chased down some of the links. I guess getting started with the second section, which is the machine itself. What's rather interesting is that they kind of broke out their implementation of the Smalltalk's virtual machine into kind of 2 rough sections, right? There exists the virtual machine in production mode, which runs the code, and it works as you would expect of any virtual machine implementation in virtual machine system. You give it some code, it runs it, everything is great. But alongside this, they have their own simulated version of the virtual machine, a virtual machine inside a subset of Smalltalk called Slang. And inside the Slang machine, they have a deterministic. The important thing is that it's deterministic. So they basically have Smalltalk and Smalltalk, so to speak, a very small subset, but it still Smalltalk. It's closer to C than Smalltalk, but it's still there. And it's deterministic in that they in order to kind of simulate effectively and to give proper debugging, they had to make sure of a couple properties of their virtual machine. One is that they can have deterministic addresses. So when garbage collection happens, normally all the addresses in memory get reshuffled, right? All pointers become invalid in a normal language. Everything gets a new pointer. In this deterministic virtual machine, they can't do that because they want it. They don't want it to have address randomization to happen. So you have considerations like that. You also have that every instruction also increases some synthetic counter. And that way, you have no timing issues. So they've done a lot of interesting things to make it kind of be compliant. Another technique that they discuss is that if you look at how the memory is laid out in the virtual machine, in the C production system, as they call it, it's some big malloc region, some mmap region, where they have text data, they have some machine code zone, and the young generations as you start getting further and further in to the memory addresses. But the Smalltalk, the simulated version, is not quite the same. They use a byte array on the Smalltalk side, and this covers the machine code all the way to old space, but it does not carry the JIT, the garbage collection, the simulation interfaces and all that. It can't call those directly. And so if any code were to call it, it would be an error. Because they couldn't model it fully and nicely by the sounds of it. But they do this interesting thing. Since Smalltalk has a condition system is simply when You throw an error, the stack doesn't unwind. Instead, you can do something about it. They've implemented a condition handler to see if it's one of those special addresses and like deal with it properly. And that way, when you compile code one way or the other, you don't have to change it based on the simulator or not. It just knows that, oh, hey, these addresses are special in some way, and they protect it as such. The machine has a lot of other interesting systems, though I think I would want to talk about that in like section 3. I think we can kind of get to section 3, which is their experience reports, because the rest of the features will be covered there, I believe. I guess in the experience report is where things kind of get interesting. They had to deal with debugging the system. And so there's a few really cool tricks that they had. One was the initial JIT development. So one way that they described debugging the system was that the JIT is incomplete, right? The JIT's not finished, but yet they want to test it and make sure it works. And so in their non-production system, in the simulator system, what they could do is replace the JIT with their new JIT. And if there were a bug to occur, or let's say an instruction that it doesn't know how to translate, Smalltalk would throw a does not understand message, and you can edit it, fix it, and then have the code continue running. This should be familiar to anyone who's used Smalltalk, because when you develop a function in Smalltalk, they talk about developing in the debugger. So what this means is that you can develop the JIT, something which is important to the base development inside Smalltalk using all of the Smalltalk tools. This means that you have a lot of interpretations of how it goes, and they described later that if there were a bug in, say, the JIT, it were to say create incorrect code, you would be able to stop it and then rerun the JIT on the method in which you were compiling until it looks correct by changing what the code does and regenerating it. And there's actually a really cool video linked, though. Yeah, they have a really cool video linked on page 8. There's a 30-minute YouTube link, and if anyone's curious, the guy shows in 30 minutes having some code which crashes. He wrote a JIT which crashes the system. So what he can do is there's an important feature called a snapshot, which he uses. This is another important feature with the Smalltalk image and with their environment. They're able to take a snapshot of Smalltalk. So you run it up to a point, you save it to disk. So that way when you load it, it's immediately at the code there. So you're able to snapshot the code like right before the error occurs, and then you can go from there. And so he shows off doing that, along with setting some breakpoints. And what's neat is that because it's all on Smalltalk, they've made a lot of visuals. It's forced them to make visualization tools of like, well, I really want to know what this annotated address goes to. So they're able to dump the annotated address so they can see that the pointer which goes wrong is in new space, and it shouldn't be, right? It gets wrong, and in the video, he shows being able to effectively dumping that information and like fixing it while trying to figure out which method, because an issue with a JIT in an inliner is that it inlines a bunch of functions, and so it's kind of hard to see. And so, that's one example. There's other examples as well where they talk about like lemmings debugging, where you can take a snapshot and then like you can basically check if a certain register is touched. So you run it up to a point, you break, and then you do a conditional breakpoint after that for seeing what memory is touched. So the machine has a lot of really interesting features that allows that type of functionality to work. I guess another interesting part besides just debugging is that having a system in which you can query and make representation of data easily and query the system for data is that they were able to see hotspots in the machine, like how many call sites were monomorphic, polymorphic, or what they call megamorphic, which just means that there's more than, say, 6 polymorphic calls. And so, they can't close polymorphic code it, stuff like that. And they were able to ask it, they claim, within an hour and see how many sites would get prematurely promoted in their optimizations, and even compare their open polymorphic strategy versus their closed polymorphic strategy, which has different performance characteristics and different implications. They're able to ask this question much quicker than a normal compile, test, run cycle, because again, the system's always live, right? You never have to like compile, run, and that just gives you fast ways of communicating with the system. So that's like, I think, a good summary of section 3. I probably skimmed over some details, but I think that might come back in probably discussing the discussion session. And finally, there's like section 4, which is quite brief. They talk about related work and about issues. Like the system's really slow, and you can tell if you watch that 30-minute video, you can tell even on a MacBook Pro, their simulator is horribly slow, which does seem like an issue when working. It's still better than nothing for sure, but I think that is a huge issue.
Well, their simulator also goes down all the way to the level of like emulating the underlying CPU.
Yeah, they wrote an entire CPU emulator. That's true. Yeah. Well, yeah, I agree. But something interesting is I think they could probably get some speed up. Like they mention in a related work, they mentioned the Maxime inspector. They seem to do a lot of simulating as well. It's Java in Java. It's a metacircular implementation of Java in Java, which is quite impressive. And if you look at their website and all that, they can actually inspect Java objects and Java memory layouts in Java. Now, it's not a fully interactive system because it's Java, right? It's kind of a mess to like work through, but it's quite impressive. And their inspector seems quite good. So I think maybe some more tooling could be made on that front.
Yeah, one thing you can do is collapse layers of virtualization.
That is true. Do you know like any techniques or projects that's done that, or like just kind of like a technique?
We did it on Orbit. Like you have the VM level knock interpreter, and then you have the software one that does things like implement extra instructions and so on. Mm-hmm. But there all these, you actually get like 3 or 4 layers of it in reality, but we just collapse them and sort of short circuit it by calling the same underlying VM interpreter instruction every time, because we recognize that this is knock on knock, so we can just skip a level and just use the bare metal interpreter.
I see. And that's not something that they could do here. Like I know that they can like skip some specialization, like they mentioned before, and how they debug is that they get close to the target and then they set up the step by step where basically, does any instruction touch this memory location? So that way, like it's like horribly slow. They mentioned that it would take like days to simulate something if they just ran like that, because, well, oh boy, you have an entire simulator from the boot up, so you just don't do that. They don't do that. So is that similar? Or I think yours is probably, it sounds like it's more efficient on the knock and knock version, because here they're simulating the queue, and you don't have to.
Yeah, it's just, well, we have a fully general mechanism for skipping naive evaluation and just going to some optimized version in C. And you can use that to collapse all of the layers of virtualization as well.
How do you, can you still do that with like tracking information? Like say, if something writes this memory address, stop, or would it interfere with that level of debugging? Or would that just be a different mode?
It would interfere, yeah.
Yeah, I see. That makes sense. And then I think more layers here would probably make sense for like practical usage of it. It seems like a lot of the benefit in the system is just trying to avoid the compile run cycle, because it's horribly slow in comparison, and you just don't have your data in front of you. I think a really good win in the paper that they show, and if anyone's watched the video, is that you can just like dump any part of memory, and you can have like the IR layer, kind of how that works in like the assembly which it generates, along with anything else you want. Like it's not in the Smalltalk system, but I've seen control flow graphs of say factor, where you just like model the CFG with a something is graph viz, and it just looks wonderful to like trying to understand like how it works. Yeah, that's basically the paper. Does anyone, I guess, have any like questions or discussions about any section or anything like the paper talks about but doesn't go in depth? Like I read like let me tell you about like build me a JIT as fast as you can. Like I read that today in preparation. If anyone has like any questions about any part of the paper or things that I skimmed through. Yeah.
I suppose the most immediate practical question on my mind is, what do you think we should steal first?
Yes. I think a lot of it. I think some of the architecture decisions are quite good. I think because they have Smalltalk and Smalltalk, it's quite powerful. There's a different paper, not this paper, but there is a paper called Squeaks, Back to the Future, and it talks about the Squeaks development. And this Open Smalltalk virtual machine, I think, is derived from Squeaks or something similar. So I think like it's the same virtual machine because I know Pharaoh takes it from Squeaks, and this is what Pharaoh uses. So I believe this is an evolution of Squeaks. And in Squeaks, they got the original interpreter out in 5 weeks. So they made a Smalltalk from scratch in 5 weeks, copying a lot of code from the Blue Book. And then 6 weeks later, they got it self-hosted. So it seemed like they had a bunch of runtime stuff in like C, I want to say, and then like got a Smalltalk, bootstrapped Smalltalk compiler.
I like that they were able to do the JIT in like the test-driven development way.
Yeah,
it's like
that is nice.
I mean, when Kent Beck coined that, he was just a Smalltalk guy trying to export things from Smalltalk culture.
What do you mean? Like you see that in other projects, or?
I mean, when Kent Beck started marketing test-driven development as a thing,
really?
he was just trying to export Smalltalk culture, basically, since you can actually do that in Smalltalk. You write the test first, and then every time it fails, you just implement the method that it failed at because it didn't exist, and then you're done.
You know, that's actually quite fair. I think they talk about that in the NV environment paper discussion. So there's another discussion surrounding Smalltalk called NV, in which people worked on the NV system, which was a Smalltalk implementation and editor and all that. And often they were to just implement things like that, where it's like, oh, hey, just run it, and if it fails, go implement it, and you can do tests first that way to get kind of the API you want. Yeah, that is quite nice if they were able to do that on like the JIT level. Like I think it is quite nice. I think one thing to steal, Terrence, I guess answering your question, is you can make a probably really naive and dumb interpreter and then like replace it later. I think this has been worked out in practice in a few projects, which gives me some comfort. For example, in Factor was interpreted at some point, but now there is 0 interpreters inside the Factor compiler, right? They have a naive compiler and a fast compiler, and the naive compiler is in C, and the fast compiler is in Factor itself, right? So you could probably steal the idea of making a really dumb and naive like interpreter, and then like building your JIT on that because your language will be too slow. So I think there's a lot of optimization techniques that you can just like steal when doing it that way. And I think like just modeling the system, something similar to what they do here is quite good if you're trying to go for a proper dynamic environment.
Thanks. And do you have a sense where that would be like easiest to start integrating into widely used dev tools like, I don't know, LSP, Emacs, Lisp, whatever?
Mm-hmm. Yeah, so like one really nice thing is that you can do better with a fraction of the work. Like a lot of money is spent on making like LSP and scaling it just because, you know, that's kind of where the money's at the moment. But if you have tools like this, you just get a better environment because instead of, like, for example, I have the LSP server for ClaimD running and it's eating about 2 gigs of RAM. Every time I run Haskell, I have like 5 LSPs open because Stack doesn't work properly. And, you know, each Stack project has its own thing. But if you have just a running image, you get it for free because you can just query the package for a lot of the information, right? Like if you want type information, well, it's live in the system. You know, you just ask the system, hey, what is the type of this symbol over here? You still probably need some extra support for in-context style of information that you probably do need to expose as well, which you know, you may need to give specially, or maybe you can do it in a smart way, but you would get a lot of the behaviors for free, and you would you would have a more coherent system that just eats a lot less RAM as well. If you look at these machines, so since we read the Smalltalk paper, if you look at the Smalltalk IDE and experience, they have a wonderful class and method browser, which you can like tag things. So you get in some ways a lot better experience for a fraction of the work, just because, well, it becomes now a social issue of, well, how do we want to build our tools and how do we build things on top of, right? So what became technical is now social, in that, like, well, how do we want to design the information? Because the information exists. How do we want to decorate the information that lives? And I think a really important thing is if we abandon the file-based model, you can still dump out files, right, to hard disk for like tools like GitHub. But if you start to abandon that and you view it as an image, you can give better browsing capabilities of your system. And that's what Smalltalk does in a lot of scenarios. It's just we give it all really nice tools for that.
So the right route is just write a standalone interpreter, run it as a separate process. The LSP interface is just a message passing interface between the LSP server and the live interpreter.
Yeah, that's one way to view it. You can do other things like start up your own servers, but like if you're running generic browser editor integration, yeah, you'd probably just connect it to LSP that way. You just feed it the information just based on what you have, and then you'd probably define out your own protocol, because LSP probably isn't ideal if you have more information about your language, right? You could do things much stronger, so you would just define out your own protocol. It's why like Sly and Slime is its own protocol, and why like Smalltalk has its own thing, and like so you just define out both, and then you would say, if you want the better editing experience, you use the thing that supports whatever mode you want to work in. So you have like tiers, I guess.
Right. Okay. So that would be more like an extension to the IDE, using like the IDE's extension interface as opposed to the LSP interface.
Yeah, and so that would be like a per editor thing rather than the LSP, which would just be generic. If we don't want to write the extension for, say, VS Code or Vim, we can just say, well, you could use the LSP, and we'll eventually get to like making it better.
Right.
Yeah.
Cool. Thanks.
You've probably already mentioned this already, but what did you say was the most important part of this interactive kind of programming environment? What do you think is the most important component?
Like getting there, or like what the user gets out of this? Because I guess those are kind of different things.
I was thinking mostly about what the user gets out of it.
Cool. So I think a big thing is that you can have multiple. I think it speeds up user development by like a pretty large margin, by a pretty large factor, right? Like if we're getting into a big code base that we do not understand very well, it is very important to be able to poke and prod it, right? Like type signatures aren't enough for me to intuitively understand, say, a Rust code base or a Haskell code base. You have to kind of play with it. And being able to play with your software matters quite a bit. But further...
So do you mean like stepping through, like a step-through kind of debugging process, but you're stepping through the code line by line?
Not that per se, but more of like the system gives you different ways of viewing it. So I can jump through the code base in many different ways. It's not just a static, I look at these files and I try to think about what these types mean and how they come together, but rather the system can give me examples of how everything is used, and I can just run it wherever on the system. And so I can just interactively play with any part of the code base. So that way it becomes less of a, here's the language, I compile it, I get a binary. It becomes more like a conversation between you and the language. And so you can even ask it, hey, I want to view the application in like a graphical sort of way, or I want to view it like this. And so when you can ask it questions, you can get many different views of the same data without having to go into a test block or a main block, wait for a compilation cycle, and like get out your answer and do this for every little bit. You can just ask it immediately over the data which is live, which you have in your hand. right? You can inspect it. So I think that speeds up like understanding like massively. I'd say that probably is part of it.
So I actually agree with images, at least for debugging purposes and trying to understand how a system works. What I don't fully agree with is like the way you distribute software with images. How do you like approach this in a decent way? Like if you have a monolith of like a huge image, how do you distribute this?
Sure. It's not any different. At the end of the day, it is as bad as any batch language. So what I mean by this is that you can always go down and say, oh, hey, we have files that are right out on disk and, we ship it that way. I do this in my Lisp programs. But if you look at what, say, Pharo has, they have their own thing called Iceberg, which is just Git, right? It has its own Git interface where every method is tracked. So it has like a local history and like a Git history. And so every time I make changes, it's able to query the system, run all the tests before me pushing, run all the style checkers like you would in a modern IDE if you're writing like Java or something. Has all those features just built in. And so you get the same experience, but a bit better because it can track it across methods. And like, even if you swap what class something's in Pharo, it knows internally what the diff is. And, for Git, it'll show like a green difference because it has to move files. But on your end, it knows that like, oh, this just, nothing really changed here. It just changed what package it belongs to.
Okay.
And you can make dependencies.
Yeah. So you're not the one who's actually interacting with Git, like it's the system that's modifying the tree itself.
Yeah, you can do it that way. That's how Smalltalk does it. There's a variety of different techniques in which you can use, right? You have more freedom in how you design it. I think you can design a better Git, though, if you have this, because if you have all this information about how the language is, along with the language parsers, you can make stronger diffing tools, right? So like you could like for GitHub, you can like give out like a Git version along with like some more richer manifest differences on your system. And then you can load the more manifest difference on your system and like see greater like, oh, this entire text didn't change. It was just this one little object inside of this text. So I think you could even design much better Git systems, like style of Git systems with an image because you just have more information around.
Text diffing is sort of it's like a lowest common denominator algorithm that works with all kinds of things because least common subsequence is easy algorithm to implement, and like classic diff3 is a very dumb and easy algorithm to implement. What you want, what you want even with your C program or your Rust program or whatever is, if you could have it, you would want AST level diffing, so that, for instance, every time that you like remove a function, it doesn't confuse the LCS algorithm because you have a closing brace here and a closing brace there, and so you get some bizarre looking diff that's actually just the LCS getting confused, or diff3 getting confused. You don't actually have AST level diffing. In part, this is because ASTs are very baroque and not necessarily that close to syntactic constructions for languages like C or Rust or whatever. And part of it is just that nobody has done the work and implemented it. There are algorithms for tree diffing and tree merging that exist, but they don't get integrated. And part of the reason they don't get integrated is because of how tied things are to just like a tree of text files layout. If you have access to like actual ASTs in memory and you're using a structure editor anyway, it's a much smaller leap to go from that to running your diff algorithm and your diff3 algorithm over those structures that exist in memory.
Yeah, I guess I want to add on is that this has been done before as well, sort of. I'm not sure how good the diffing is, but on the interlisp system, which you can play online today, you have a structure editor in which you edit S expressions. And so when you save it on disk, it remembers some of the changes, and there's a versioning difference because like the file system versioned things on like nicer operating systems. So, I think they may have had like smarter diffing tools on like inner Lisp to like accompany that.
Hey, I have a question for you, Ray. Can you give me some maybe some pointers like where I can read about this tree diffing stuff you were talking about?
Yeah, I think I have some papers.
Nice. If you don't mind, could you post them later, please?
Yeah.
Oh, nice. Thanks.
Does anyone have any, I guess, other questions about the paper? I think one other thing that would be, I guess, important to kind of like see is like how you kind of get there. Like it's actually kind of interesting that they're able to like model it in this way. I just would be interested in seeing, I guess, more systems like this. I don't think they're necessarily all that complicated either. I guess one thing that you probably should steal is, I don't know how big the C runtime of this system is for the actual production VM. I suspect that the object, the inheritance system and all that probably is quite large, but I know that this can be done could be done much more minimally, because if you look at like, say, the factor system, they managed to implement their entire virtual machine in like 10,000 lines. I guess some other questions is can this compiler bootstrap itself? Because some virtual machines can't, right? They expect an image which exists, and they talk about it here. Unlike a conventional language, you usually have, say, some kernel in which language exists, and then you hack on that image, right? So you're hacking on a bootstrapped image. And so I'm not sure here. I don't think they mentioned if you where the starting image comes from. Actually, you actually don't know in the Smalltalk case.
Yeah. Usually you handcraft, like you handcraft a base image that can compile, a full starting image.
Yeah, but I'm like, how do you do that? Do you do that with like a dumb interpreter at first, or how do you do it? Because like,
so yeah, you do it using a dumb interpreter at first, but like this is a one-time bootstrapping process because you just once you have the full image, then any future versions can be constructed using that previous image. So like this is a one-time hand rolling thing, and then after that, you just have the full system, and you can use the full system to generate the tiny bootstrapping system easily.
I see. So even if you have like massive data changes, you can just replace it that way.
Yeah.
Makes sense.
And you just keep like a very tiny bootstrapping system that can run a bunch of code to get you to the actual like starting image that you want to distribute.
Yeah, that makes sense.
You can actually look at how Emacs does this, which is really Baroque and Byzantine if you want to give yourself a headache.
Yeah, I'm good. I know that there's special flags in GNU C for doing it, isn't there? Like, which you'd
There is, yeah. I think they might have finally removed it, but there was this thing where you could just dump. glibc had a function that was only used by Emacs that dump this process's image as an executable rather than like a dump. And that's how Emacs was always packaged and distributed. I think that might have been taken out of glibc and just given to some Emacs specific thing because the glibc maintainers hated it and Stallman liked it because he only cares about Emacs.
Nice. Is there any difference than just like, say, dumping it and then doing a write on it that makes it executable? Like, I know that when you nmap some memory, you can say like you have rights to execute it.
Yeah, there's
something
differences. For one thing, glibc is extremely dynamically linked, right? Like there's no way you can statically link glibc. So there's considerations in terms of dynamic objects. I think, and then like there's headers and so on that you need to be an executable. But yeah, in principle, there's not too much of a terrible. There's not like too much terrible stuff involved in dumping something to executable. It's just all of the platform specific details, of which there are a vast amount, which is kind of why glibc didn't want to have to maintain this for various platforms.
I see.
But Stallman has a lot of power over the GNU project, so I think it was only very recently removed. If it even was removed, it might still be there somewhere.
That would make sense. I'm guessing. I'm guessing Musa would never have that.
Yeah, no. But
I
like
think
when you have an image-based system, things like, I mean, like on exec is kind of your standard thing, right? Because when you have an image-based system and you stop running it, you just, you dump the memory image and just restore it again, which is not quite the same thing. There's still like a VM shell that you run to do this, but it's close to the same thing.
Yeah, you just mean like overriding like the running system, so that way when you go back to it, it's resumed where it is, right?
Yeah, just modulo being a Unix executable with elf headers and so on.
I think that idea can be pushed. Like oddly enough, like the only image system that I use out of the languages I use, like Smalltalk, actually does that. Every time you can save your working directory. But oddly enough, when I work in like common list or Factor, you often actually don't save. Like you can save a new image after you load some stuff and like dump it. But often I just reload my libraries into it because they exist. Like the system knows where they exist. I just have to load the code back in because it's not that long. I think one thing that could probably make that more practical is if you had like a base image in which you forked off of, which doesn't have your library loaded, and then you have like a version where your library is loaded. So that way, say you accidentally leak some resources and you don't feel like going through the processor and like manually removing some processes that you know about. Maybe you can like load up the old image, check all the processes that load, and then like do a diff and remove. I think smarter snapshotting should be had in a lot of these systems that I think a lot of them just don't implement for whatever reason.
Yeah.
Because I guess another thing which is interesting is that everything on these image systems are recorded. So like in theory, stuff like Git probably just comes for free if you just know that, hey, these objects once existed, they now belong part of a project because they're already being backed up. So I think there's some things that you can do that would give you like, I wrote some trash code, but I actually want to commit it somewhere. So now I still have the history of it because it still exists in some shape and form.
Yeah, especially if you just run your image as an event log, right? So it's a login checkpoint system.
Yeah, I think there's a lot of interesting things that can be had with login checkpoint systems. Like even in the paper, they mention quite a bit about, oh hey, we can just up and replace the garbage collector. And so what you do is you make a checkpoint of like everything makes sense in this state, but I want to test this function with my garbage collector, but I don't want to run it on the startup because it would trigger earlier than the test case that you want to like test it on, right? And so what you can do is you can replace it at any point. And it's like logging and checkpointing there is like, I think, invaluable for actually doing work. I mean, like real work on like, say, the garbage collector or even the JIT. So that way you're not running into like code that you didn't expect to be had with the new code.
Yeah.
But yeah, I think there's a lot of boon to be had, especially with data visualization that just simply is not had with like non-image systems. And I think that's like something that's important. Yeah, I think you can really push things far, quite far with these techniques.
Yeah, I think the techniques are pretty cool, and maybe you can keep on extending them. But I feel like maybe in my mind, I feel like maybe there is a certain subset of them which give you 90% of the benefits, and then
Well,
maybe the rest of it may not have as many gains and may be harder to implement. But then,
maybe, but like, so the thing that is unnecessary is the VM in itself per se. That allows you to debug the virtual machine as if you can debug user code. And they mentioned themselves, like the original implementer of this was quite skeptical that they could do it in Smalltalk, because he had experience before working on the I forget the name, but there was a Smalltalk, a fast Smalltalk before that, in which, you know, he was quite skeptical about, because, you know, he worked on it before, but he ended up finding that doing it in Smalltalk itself was much more enjoyable, because when you are developing a virtual machine like that, all these extra things actually just allow you to work on that faster and work on it. You know, it's the Deutsch Switcherman VM, which was written in C before this, which I think there exists a book about. But an issue is like, you get a lot of the benefits just by being image-based for end user development, right? If you're not hacking on the VM, as long as you're image-based, you get pretty much all the benefits. The issue comes in, like, say you want to replace parts of the VM yourself as a user, which isn't as absurd as you think. Some fundamental parts ought to be replaceable. And if users have special workloads, you should be able to expose the user to being able to change those systems easier, right? Like, for example, I believe that you should be able to change out the garbage collector whenever you feel like, you know, as long as you have standard protocols for how things cooperate and incorporate with each other, you ought to be able to do it, as long as you fulfill some type of interface. But in doing so, like, you just, like, the important part is that it's image-based. And so things being metacircular just means that you get even more benefits, right? Like, for example, in the paper and other projects, they mentioned the Maxine Java inspector. And Maxine is Java written in Java. And what's really neat is, because it's Java in Java, you can look at any memory address, both as like the assembly code in which it is and the memory layout which it is, but you can also view it as the object, and you can inspect there. And so if you're trying to like understand how its memory model works, or maybe even work on it, you know, it helps being metacircular. It's not necessary, but I think it makes your life easier. You don't have to wait around for compiling anymore, which is nice.
I see. Just one small question. I'm not sure if this has been asked already, but is there something special about Smalltalk other than it being small, which makes it particularly applicable for this purpose, or any language used?
I think any language can do it, but there is a few caveats. One thing is, you want your syntax to be simple. The reason why you want it is because you're going to be implementing it at a lower level than you're used to, right? So if you have some monolithic syntax, like an AGL-like or an ML-like, it is much harder, just because, great, now you have to write a parser for this, either at like the VM language or at C, and you really don't want to do that. It's just more overhead than you want. But any language should be applicable. I guess one thing that makes Smalltalk nicely fit for it is that the language model is good, right? For example, you don't need to make modules. So Smalltalk doesn't have a great object system, in the sense that I think it has issues at scale. There are systems which address this, like Newspeak, which have a nested system, which, you know, you can view it as like nested modules. But an important, I think, idea is that if you have like an object system like Smalltalk, this gives you your module system for free, because you can model objects, you can model modules as objects. You have one less idea to implement, right? And so by keeping the amount of ideas in your language smaller, you allow the system to be implemented much easier. You can technically do this in anything, right? For example, they use a subset called slang, right? So if you have a non-extending language, what you can do is you can write in a subset of whatever big language you're writing in. Use that to develop the machine. If the language can extend itself, you can then extend the language to the the user-facing one. If it can't extend itself, then you implement that as a layer on top, and it's a bit sadder. But it's all doable. I'd say anything which can extend itself just has an inherent advantage of being implementable in general,
Makes sense.
right?
Because everything reduces down to a set of primitives. I understand.
Yeah, exactly. And you don't have to introduce this weird notion of the user can't write this, but we can, so we must design a system which allows these certain constructs, right? Smalltalk never extended the language. That's why in the paper it mentions that Smalltalk is an object system, not a programming language. And I have no interest in exploring how languages extend. And so that's why Smalltalk can fit on a postcard, and what you see is what you get. It's flexible enough to derive everything that you care about, along with having a meta object system, which gives it better dispatching, because you can do dispatch on kinds, and then you can do dispatch on a lot of really nice ways that you can't in other systems. But if Smalltalk could extend itself, then you could add new syntax to it. If you want to add pattern matching, go ahead and add pattern matching. For example, Factor is a stack-based programming language. Lexical variables and dynamic variables are encouraged, and lexical variables are considered proper over some stack-based constructs like rot. And they managed to add these as macros because they added a really good reader syntax ability. So if you have some way of extending the reader, you're able to write these new constructs for free, because you just need to make one reader extender, and then everything else kind of falls off if you use good abstraction principles. So I think just better language design, to be quite honest.
Fair enough. I understand.
Yeah. I guess to give one final example, Maxine is Java in Java. Java is a complicated language. It's not a simple language. It's not like Smalltalk. Smalltalk's classes were derived from meta objects, and meta objects derive classes, and it derives a whole bunch of behavior. Even messages are objects. In Java, this isn't the case. You have this hard separation between classes and objects. You have instance variables as a real thing, right? Smalltalk, they don't exist. Smalltalk, almost nothing exists. It just falls out of the model. Java is a big, complicated beast. Yet they managed to implement Maxine, which is Java in Java. So that shows you pretty much anything's possible. Your language may not make it friendly to play with afterwards, because some decisions make your system inherently less friendly in a interactive and user-friendly environment than others, but that's, I guess, a side question.
Cool. No, I understand. Thanks.
I guess I'll leave some notes on one final note. There is extra work to be done in terms of FFI support. I think FFI is important to design no matter what, just because you have to deal with the host operating system. And because of that, I think designing the FFI in the modern era is probably important. And I think, oddly enough, I think the languages which are image-based have done a really good job, at least Smalltalk and, not Smalltalk, but Forth-likes and Lisp-likes have done a really good job there. And I think those are probably worth stealing when having to communicate with this operating system, which Smalltalk seems to have some issues with, or it's not as native. They mention issues in section 4 or around those points. Great. I would like to thank everyone who came out today to the meeting. I think here's probably a good stopping point. I'm going to be posting this online because there's some people outside the organization who would want to view this. And I don't know, I think it's good to have people talk about Smalltalk and whatnot. I have not decided on the paper for 2 weeks from now or whenever we can schedule it next. I'm thinking maybe the self paper, which was a Smalltalk derivative, which talked about more efficient ways of doing things. That could be a really interesting read. If anyone has any suggestions, feel free to leave it in the languages research channel. And if you're outside the organization, just ping me with papers, and I will consider them and I'll add them to a list somewhere. I'm hoping we can continue and we get through a lot of interesting papers and I guess understand systems to a greater level. But with that, I wish you all adieu.